All right, we just discussed a technique for route summarization in such a network. It can be done manually, allowing us to freely summarize some detailed routes into the summary route entries we desire within a fixed range, to reduce the routing entries in our device, thus also reducing the resources consumed when our device queries the routing table and performs forwarding. Next, let's talk about another technique within the EIGRP environment. Is it possible for such a scenario to occur, this situation? Suppose we have a boundary router in this network. What boundary? It is the boundary between one IGP protocol and another IGP protocol. For example, this network, on the left, we are running an EIGRP, a distance vector, dynamic routing protocol environment. Left side is EIGRP. On the right, we are running another dynamic routing protocol. Suppose on the right, we are running OSPF, a link, state dynamic routing protocol environment. Right side is OSPF. Now, what is the problem, students? Only this middle router. Let's assume it is R1 only. R1 has all the routing entries from EIGRP on the left, and it alone possesses all the OSPF routing entries on the right, other than IT, the other routers, such as this R2. It only has EIGRP routes. It does not have any OSPF routing entries. This router on the right, say R3, it only has OSPF routing entries, no EIGRP routing entries. Meaning, apart from the middle, R1, it can access both sides. Other devices can only access their own side, the same dynamic routing protocol device. So, if we now have a requirement, we need our EIGRP devices to be able to access OSPF and OSPF devices to access EIGRP. How should we do it? How should we do it, students? There are two technologies that can help, two technologies that allow us to achieve this. The first technology is called redistribution. The second technology we can use is what? Through a default route. Isn't it a default route? Suppose we tell all routers within our EIGRP that to access the 0.0.0.0/0 route, you access any destination regardless of prefix or mask, meaning all host addresses. If you, R2, can't find a route in your detailed routing table, then send the packet to me, R1. Similarly, R2 could also provide a default EIGRP route to the routers behind it. Then those routers will know whenever they access any host address and can't find a detailed route in their routing tables. To send everything to R2, similarly, we all can know if our boundary router, AR1, can distribute a default route through EIGRP to all routers in our network, then everyone will know that to access another network, which is not present in my routing table, this unknown host address, I can reach it through the boundary router. R11 said R1's routing table has OSPF routes. I am a boundary router. So, of course, R1 can facilitate packet forwarding and can reach all hosts in the OSPF network. Meaning, once R1 issues such a default route via EIGRP, we can unilaterally from EIGRP access the OSPF on the right side. This is the characteristic of a default route. Of course, we can also let R1 distribute a default route to our OSPF area. Then they, when accessing any destination, can go through R1, the boundary router. R1 has all the EIGRP routing entries. In turn, we can also access successfully. What about this kind of default route distribution? For a network's boundary, from one network with a dynamic routing protocol. Accessing another network, isn't it very convenient and special? Letting our boundary router issue us a default route. All devices in our network will be able to send packets to the boundary router through the default route. The boundary router, having routing entries of other networks, with such dynamic routing protocol entries, send to our other network students. This is a special use of a default route, so we need to master a technique on how to allow an EIGRP router to issue a default route to our entire EIGRP network, allowing them to access host addresses without detailed routes, send the packets up to our boundary router. This is the technology we need to master. So, injecting a default route into EIGRP. This is the first point we are discussing today, not the third point, the third point. So how does EIGRP inject a default route? Let's say R3. We are a boundary router in the network. We, 10, 13.3 minus 24 boundary router. Now, there's this requirement hoping R3 can provide our network's R2 and all devices in our network. All devices connected to R3's network with a default route. Allowing R2 to access any destination via R3, R1, of course, can receive routes given by R2 default route, who goes through R2 in this way. All routers within the network can send packets up to the boundary router R3, then R3. If behind it there's OSPF EIGRP and BGP can throw it out, isn't it, students? This is our requirement. Then EIGRP issues a default route. EIGRP issues a default route. Then how to issue first for R3. The first option, then since we want to advertise this EIGRP route entry throughout the entire network, doesn't it mean that R3's EIGRP database table needs to include a default route? Yes, students, actually, the key to EIGRP generating route entries is by calculating the data entries in our EIGRP database and then converting them into routes to be reflected in the routing table. So R3 just needs to do this. Insert a default route into our database. Then, of course, it can, through EIGRP's distance vector routing protocol, communicate this database entry to our other EIGRP neighbors. Then they can generate a default route. So the first simple solution is through what? By announcing a default route via the network command into EIGRP's database, using EIGRP's distance vector dynamic routing protocol operational method to exchange database entries with our neighbors, thus causing the neighbors to generate such a default route. So on R3's side, we can do this. Let's try to see if R3 writes a default route. Then I arbitrarily write an exit interface IP route 0.0.0.00.0.0.0 exit interface arbitrarily write. For instance, write loopback 0. Sorry, can't write like that, writing like this. I'm afraid of misleading. Remove it. We first put a next hop IP route 0.0.0.0.0.0.0.0. Suppose we write a next hop address 10.10.3.4. Then in the routing table, due to R3's loopback 0 interface, having a direct route, 10.10.3.0 just happens to be a direct route. So the default route, we just wrote next hop, address 10.10.3.4, has a direct route, accessing the network segment, destination address 3.4 has such a direct route 3. 0.24 then has an exit interface, a loopback interface. So for R3, the next hop address of this static route is reachable thus. This default route is effective. Now our R3 announces this default route into our EIGRP to see if it works. Does it work? Show IP-AGRP topology. Is it possible? No, so you see we cannot announce this default route into our EIGRP database. Students, we cannot announce a static route into our EIGRP database. So you're saying this method doesn't work. Just putting the default route into our database, I could then tell R2 and R1 via EIGRP database transfer. But it doesn't work. But let's try another method. Students, let's try another way. No IP route 0.0.0.0.0.0.0.01, 0.1, 0.3.4. Delete this default route. We change the way we write it. Router EIGRP 90. Sorry, first IP route 0.0.0.0.0.0.0.0. We attach an exit interface, loopback 0 static route with an exit interface. But now what? Now it's a default route, a special static route with an exit interface. So this is a log message, a hint saying this is what? A default route. So there is no gateway, right? So if it's not a point-to-point route, what might it cause? Might it cause a loop, right? It could affect performance. There might be a loop, right? Let's give it a try. Announce this one with router EIGRP 90, the default route, into our EIGRP database. Look, is it there? Yes, do you see it? There's a what? A default route. That's not right. Right, students? Why is my static route and this default route following a next hop address not allowed in? But it comes in with an exit interface. It came in pay attention. Students, when EIGRP processes a default route, then write a static route. Write a default route following what? An exit interface, then through the network command, announce the default route. Is it possible? But why must it follow an exit interface? Have you ever thought about this, students? Why is that? It's actually quite understandable. Students should think about what is the main purpose of our network command? What is its main function? We often talk about this. What is the main function of the network command? The network command. What is it for? To activate interfaces, to make interfaces, operate dynamically, and what else? To make interfaces. The network command matches corresponding direct routes put into the database. Let's take a look. At this moment in R3's routing table, this one, we follow a static route with an exit interface. How is it written? What is this thing? Do you see it? This static route, when paired with an exit interface, how is it written in our routing table? It is a direct connection, students, meaning that any destination address, these host addresses, are all on the direct link segment connected to our loopback 0 interface. This is a static route, paired with an exit interface, the phenomenon it exhibits. You might as well just look show IP route 0.0, 0.0/00.0.0.0 static. But students, we paired it with an exit interface, right? It is directly connected. It is a direct link, meaning that the destination address I want to access is all on my loopback 0's direct link. Now, recall our network command statement activating interfaces, making the corresponding network command subnet, matches the direct route, put into our dynamic routing protocol database. We actually caught a bug, right, students? But it's not a flaw, it's designed that way. Through what? Through static routing with an exit interface, it gives a direct connection, this kind of connection. Because the destination network segment is on our interface's direct link. We bind the interface. This situation occurs if we follow the next hop address, such as an IP address, IP route, such as 10.10.5.02.5.25.25.0. We follow the next hop address, show IP route. There is no directly connected, just something else. No. Do you see the difference? Students, so theoretically, when it comes to static routes, when we pair it with an exit interface, we have a method to get our static route announced into our EIGRP database. This will also be covered later in our discussion on BGP, a path vector routing protocol. As we study our external network protocol BGP, we'll find that we can put route entries into our database, and then our external network protocol acts as a carrier of route entries, transmitting them to our other devices. Students, remember, if you need to announce such a default route into the EIGRP database, the default route must be paired with an exit interface and not with our next hop address, because that's a peculiarity of static routing, a unique distinction. Pairing with an exit interface means that the destination network segment is on the direct link of my interface. If you pair it with a next hop address, it doesn't write it that way. What does pairing with an exit interface mean? It indicates that the destination network segment is directly connected on my interface. If you follow it with a next hop address, it won't be written like that. Okay, students, delete this. Then use the network command to match interfaces, letting the interface's corresponding direct route be announced to our database. But you need to be aware that the main function of the network command is to activate interfaces. Now, our network command, what is activated? Show running config section router. EIGRP. What exactly does our network command activate? 0.0.0.0, all subnets. If we do this, remove 10.10.3.3. Remove 192.168.23.3. Remove network 0.0.0.0. When we do not run EIGRP, neighbor relationships will drop. you need to be aware that this command is like a double-edged sword. You use the network command to activate our interfaces, letting our interfaces correspond to a default route, direct routes put into our database, including the default route. So this statement has a broad scope. On R3, what do you just need to do in your EIGRP? Network 0.0.0.0, all subnets, students. It's like we're network mining, matching all subnets with interface addresses matched by subnets causing interfaces to run, dynamic routing, EIGRP, direct routes, put into the database. With this operation, you only need one sentence. Show running, config set router, EIGRP, all interfaces on this device will be matched. All interfaces direct routes will be put into the database. So, in one sentence, make all interfaces on R3 run EIGRP, all direct routes, all put into the database. Then we will directly establish EIGRP neighbor relationships and directly send and receive our database entries. Look, the default flow is directly brought in. So here at R2, show IP route, look inside the routing table. We learned about the EIGRP route entry transmitted from 192.168.23.3. However, this EIGRP route entry is quite special, marked as new, what a candidate default route. EIGRP neighbor gave me a default route. So R2 has received from R3, a database entry, a default route. Of course, I can do what? Pass it to our EIGRP neighbors, spreading the message far and wide. R1 can also receive R2, giving us the EIGRP database entry default route. Via R2, look at the routing table extracted through such an operation. Look, we let R3 announce an EIGRP default route to all of us, EIGRP devices among hosts, these routers. As long as running EIGRP can receive the default route from R3. Look, for example, R1. We access 8.8.8.8, the default route. Look, no detailed route goes default. To R2. R2 accesses 8.8.8.8. No detailed route goes default route to R3. Look, it falls to the border on R3 to let R3 forward through the routing table. This is the specialty of issuing a default route. So the first plan, by writing a network command line, matches the default route issue. This is the first plan. So the second plan, then write a default route. What is this? Write one default route, then through redistribution announce it into EIGRP's database, students. This is our first encounter in the entire dynamic routing learning process with this concept of redistribution. What is redistribution? For example, let's consider the same environment. For R1 on my left runs EIGRP on the right, runs OSPF, so two different dynamic routing protocol networks, and only R1 is in between both networks. I can have all the routing entries in the whole network. So in order to connect our two networks, your EIGRP can access OSPF, OSPF can access EIGRP. We can use redistribution. What is redistribution? The definition of redistribution is simple: to take one protocol's database entries and introduce them as external routes into another dynamic routing protocol. That's redistribution. How do we do it? On our R1, we can take the OSPF and simultaneously in between OSPF and EIGRP, I can take these OSPF dynamic routing protocol database entries and bring these routes into our EIGRP. But students, in our EIGRP environment, these OSPF route entries, they are not native born and raised EIGRP routes. They are outsiders from another dynamic routing protocol entering our OSPF routes from other dynamic routing protocols into our EIGRP routes. We must give them a specific identity. So you are outsiders, not our native EIGRP route entries. So when we bring a protocol's route entries into another protocol, we introduce them as external routes in the form of external routes. What are external routes? They are like locals and foreigners. When introduced, we tag them. You are outsiders. You are foreign personnel, external route entries. Similarly, we can also bring EIGRP route entries all into our OSPF, tagging them as external flow. You are outsiders. then R2 can know our OSPF route entries. Our OSPF routers can also know our EIGRP route entries. They might be foreigners, but now we can recognize them. Before, only our R1 was between the two. We could recognize everyone. Now both our R2 and OSPF routers can receive these external routes from other dynamic routing protocols. They can now communicate with each other. Understand, students. So we can bring one routing protocol's database entries into another protocol, allowing them to intercommunicate. That is redistribution. We can bring one protocol's database entries into another. Then both can communicate. This is redistribution. If we want EIGRP to inject a default route, we can certainly use redistribution. How do we do it? For example, on R3, we also wrote a default route. Now, let's not go network router. EIGRP 90 remove network 0.0.0.0. We will reactivate the interfaces. No longer using this declaration method, who else? 10.1, 0.1, 0.3. Young students. So first, as usual, this default route still has to be associated with the initial interface. So on R3, we previously declared through network command. We didn't delete our default route. It still exists, the 0.0, 0.0/0 default route. Now we do this using redistribution router, EIGRP 90. We redistribute what? Redistribute static. This redistribution static, different from what we just did. Students previously, the network command put our interfaces directly connected routes into it. But now we redistribute. Introduce, bring another protocol's route entries into our EIGRP. This is called redistribution. What am I doing? Static routes. All the static routes on this R3 device. All static routes. Database entries. Static route entries. All of them. Bring them into our EIGRP. Which routes? Take a look, right? Show IP route static. What static routes? Isn't it you, right? Bring all the static routes in R3's router into the router as external flows redistribute. Bring them into our EIGRP. Show IP EIGRP topology. A new entry appears in our database 0.0, 0.0/0, this default route. So, the database introduces an external flow. How do we see its characteristics? How to view it? Show IP EIGRP topology 0.0/0. Look, you see what it is. It is a external. It is an external route, announced by our R3 as an external route. A foreigner, not our own EIGRP, through something network mini-line declared local user route entry. It is an external route. After telling R to, look, show IP route. What appears in the routing table, EIGRP route, EIGRP default route. But it has an extra parameter. What's it called? Called external. It's external, isn't it? EIGRP's external route. So it's not native to our side. EIGRP route. It's an external route. Because when R2 receives the database entry, we can see the attributes of the entry. You see, when R2 receives the entry, R3 announced as an external route. Not a local. It is an external route entry. Although it can be brought into our routing table, but as an external route, it's treated differently than our internal routes. If our routing table has both this 0.0.0.0, our internally generated default route, what's the administrative distance? By default, we've said EIGRP route, entries admin distance. For internal routes is 90. Our own transmitted route, admin distance 90. If you bring foreigners other route entries into EIGRP, we treat them specially. They're treated differently. What's the admin distance for outsiders? What's their admin distance? So if we have the same prefix, same mask, but different next hop route entries, comparing an internal route with an external route, it's definitely what? Our own internal route is prioritized. External routes, they have a specific administrative distance of 170. Although this default route is usable, it has a higher administrative distance. No, although its administrative distance is high, this default route, since it has no competition, it is usable. It can be properly submitted to the routing table. Look, R2 has a default route given by R3. Similarly, on R1's side, we can certainly receive the EIGRP external route announced by R2 0.0.0.0 via R2. So this is the second method, redistribution. So write a IP route, default route with an exit interface. Then we go into EIGRP to redistribute the connection. Redistribute static. So what's this plan? Write a static route, then router EIGRP 90, declare the default route, declare all interfaces to run EIGRP, and correspondingly bring the mystery plan in. Okay, classmates, these are two methods, but actually there's a third method, aggregation. Aggregation can also generate a default route. How does it work? Let's do this at R3 here. So with the aggregation method, it's quite special. We don't need such a default route. We don't need to specifically write a default route in our device. We also remove redistribution, remove static redistribution. So the third method is the most, how do I put it, simple method. How is it simple? Firstly, what does summarization mean? We can take the common characteristics of detailed routes into a summarized route. We only announce summarization and stop announcing detailed routes. Even though I am supposed to announce many detailed routes, I now announce one that shares characteristics of these detailed routes. Same characteristics, such a detailed route, find their characteristics, announce one that can encompass their detailed routes into such a summarized route. We manually summarize the range, which we can define ourselves. So on R3, we now are announcing detailed routes to our neighbors, October 3rd, 10. 0.24ths, and what other detailed routes? For instance, this one, detailed route 10.3, 0.24ths. Now we should summarize this detailed route, find the common prefix and mask for our detailed routes. We can summarize detailed routes when we summarize. Can we think a bit more creatively about what summarization is? What about this default route? Can it encompass all the characteristics of our detailed routes? Can it? Indeed, our summarized default route covers a broad range. It includes all the detailed routes, encompassing all the details. All detailed routes announced by R3 will be summarized into a default route for forwarding. So in doing this, we won't make changes on R3 because the detailed routes announced by R3 are few. Let's switch locations. We let R1 announce the detailed routes, announce the default route, because previously, what did we do with R1? We had route entries for the 100 network. For instance, look here at R1, show IP route. Previously, R1 had so many route entries. Look at all these routes for the 100 network. We announce many route entries, write 007. First, we remove the summarization, remove it, and good, remove it. Now, R1 should announce many detailed routes. For example, 100.1, 0.0/24, 100.1, 1.0/24, and, for example, October 1st, 10. 0.24ths. Then we find their common features. Isn't that right? For example, we can through what summarize into a 100.1. 0.0/22 summary route. Remove these two detailed routes, announce the summary. But we can summarize a bit more exaggeratedly. We find a summary route that can encompass all detailed routes, such a network segment. 0.0. 0.0/0, which includes all detailed routes. When R1 announces detailed routes, what does it announce? The detailed routes included by the summary route. When R1 wants to announce detailed routes, what does it announce? The detailed routes included by the summary route. We summarize them away, only announcing this summary route. When I, R1, announce route entries, IP summary address, EIGRP 90, summarize all the announced detailed routes into a default route. The detailed routes matched by the network segment will be suppressed. Only the summarized route is announced. Now, R1. Go ahead. We perform summarization on the 0.0 plan. Over at R2, we can see many detailed routes, which will now all disappear. General websites are all gone. 10.10.1.0 is gone too. When R1 announces routes from the interface, all of them are summarized, turned into 0. 0.0-0, a default route. Is it coming from R1? Then R2 can certainly pass the routes it receives to R3. And R3 will also have this default route. Understand, students? Summarization can also produce a default route, then IP summary address EIGRP 90.0, 0.0/0. The cost is also clear. When R1 summarizes into a default route, on this router, all announced detailed routes will be suppressed. For other routers, we will no longer learn the detailed routes from R1 because they are all summarized into a default route. Students, this is the characteristic of creating a default by summarization. So, the difference, whether we use static routing or not, the two methods above, through redistribution and network naming, declaring a default route are different from our summarization. Two differences. First difference, summarization is announcing route entries from an interface only when it can be summarized. So, R1, only when announcing from interface 0, 0 can route entries come out. When R1, announce route entries, aggregate them into a default route. Then R1 will only send in this one direction. Constructed through my interface 0, 0, EIGRP neighbors announce the default route, and our network command line is quite different from theirs, for example, in such a network. With 4 routers, up, down, left, and right, if R1 uses the network command line to declare a default route, entering it into EIGRP's database, then we will announce to all our EIGRP neighbors the database entries of this default route. This default route will be communicated to all the surrounding EIGRP neighbors, regardless of using the network command line, to put the default route into the database, or using such a method of redistribution to place such a default route into the database. Then it will announce the default route to all our devices in the network, that is both network command line and redistribution. Announce the default routing scheme. Then, of course, there are other options. Another difference, another option, our default route summarization. On the interface, when announcing routing entries, aggregate all detailed routes into a default route. Such a plan differs from our previous network command line and redistribution scheme because such a plan, I will only announce the default route to the neighbors directly across our interface. Only to them will the default route be announced, while the routing entries announced by other interfaces will remain as the original detailed routes. Students, the scheme to generate default routes under the interface differs from our network command line. And redistribution, summarization, generating default routes, will only be towards the neighbors across our EIGRP interface, announcing the default route. But for my other interface's EIGRP neighbors, I still announce detailed routes, because the summarization happens when I announce routing entries. This is the difference between our top 2 approaches and the approach below. And if we use the network command line and our redistribution, these 2 approaches, they also differ. Network command line declaration generates routes with an administrative distance of 90, internally generated routing entries, while redistribution generates routes with an administrative distance of 170, outsiders, externally introduced default routes. There's a difference in administrative distance between the 2. Okay, students, these are our 3 approaches to generate default routes. These 3 differences. So, students, grasp this, as it will be on the exam. Students, it will be on the exam. It will come up during the DM-VPN exam. Okay, students, we need to issue default routes. Of course, there's actually a 4th type. So the 4th type, we don't support it now. Current versions don't support the 4th type, this method of issuing default routes, so we won't talk about it. Okay, students, so this is about issuing default routes. So the final point, we left off last class. Let's leave a teaser about such a 3rd division, right? The 3rd is summarization. When my router, my own router, what we announce is, for instance, 100, 1.0, 1.0-24 detailed routes, 100.1.2.0, 24 detailed routes, 100.1.3.0, 24 detailed routes. We summarize. As long as it can include subsequent detailed routes, we can suppress the announcement of detailed routes through summarization. So our range of summarization is quite extensive. All detailed routes will be included in this summarized route. I am announcing this one default summarized default route. No detailed routes are announced. So on the R2 side, we will receive the default route summarized from R1. But this approach has a flaw, which is what? I, R1, cannot see any of the detailed routes anymore, only this default route. That is the benefit of generating default routes through summarization. The benefit is simple. I only announce the default route to the neighbor directly across my interface, because only when I announce, "Can I do the summarization of detailed routes?" he will only announce the default route to our neighbor across the interface. The flaw is that if in the network we need R1 to provide detailed routes to our R, then what needs to be added? Add route leaking. Add a route leak map. We haven't discussed it now, we'll talk about it later. We'll discuss this route leaking later. This is how we generate default routes through summarization. That is, when we announce detailed routes, we summarize the detailed routes completely, summarize more exaggeratedly. Summarization is the default route. That is the way to generate defaults through summarization. 3 ways to digest defaults.